Our research, Seeing Beyond the Brain Conditional Diffusion Model with Sparse mask modeling for vision decoding, explains brain-computer interface through a deeper understanding of the visual system. Despite limited annotations and complex brain data, our Mind-Vis framework, trained on a large fMRI dataset, reconstructs accurate, semantically matching scene images from new training pairs, outperforming previous model in semantic mapping and generation quality. We also shown that, for the first time, that non-invasive brain recording can decode images as effectively as invasive measures. fMRI is a widely used neuroimaging technique that captures changes in blood flow as a proxy of brain activity, which is high spatial resolution. fMRI allows us to obtain detailed spatial information about the brain, which make it a good choice for image reconstruction. Previous work has already proved the feasibility of recovering images from the fMRI scan when participants watching static images, but the recovered images are of low semantic meaning and quality. Neuroscience reveals complex interactions in brain activity. To decipher this, we need tools that can identify patterns in our brain. This task is complicated by each person's unique brain activity. We propose using a pre-training model with a large dataset containing over 1,000 subjects' fMRI data. However, a problem arises with the limited availability of matching fMRI and image data, making it harder to learn from few examples. To overcome this, we suggest using self-supervised learning with a pretext task, leveraging the unlabeled fMRI data. Our strategy involves two stages. First, self-supervised learning on a large fMRI dataset. Second, training an image generation model using the learned fMRI representations. fMRI has some unique characteristics, including spatial redundancy due to regional heterogeneity. Also, a visual cortex has a lot higher information density, affecting encoding and decoding strategies. Moreover, when generating images from fMRI, we seek consistency to maintain semantic meaning of the original stimuli and flexibility to accommodate individual differences. Here, to overcome the issue mentioned above, we propose Mind-Vis, a two-stage framework for fMRI to image reconstruction that trains on a large-scale fMRI dataset using the sparse-coded masked brain modeling and fine-tune on paired image fMRI dataset using latent diffusion model. Stage A of our Mind-Vis model uses masked brain modeling with a vision transformer backbone for pre-training on fMRI data. We tokenize and mask fMRI patches and then reconstruct them via a VIT encoder and decoder. By backpropagation, we optimize similarity between original and reconstructed data, outputting whole brain voxels. Masked autoencoder, comprising an encoder, representation, and decoder, map input data to a lower dimensional latent representation and reconstruct it. The mask term here refers to random input data masking, enhancing model robustness and generalization. Our results show SC-MBM effectively recovers masked fMRI data. However, the reconstructed voxel quality does not directly correlate with the image generation quality. Only the latent representation is used in the next step of our approach. Our design differs from the original masked autoencoder by incorporating a biological-inspired approach, sparse coding. Mimicking the primary visual cortex, we efficiently encode fMRI into patches and map them to a higher dimensional vector space, increasing the embedding to patch size ratio for fMRI data. We use the fMRI representation to guide image generation, with double conditioning on cross-attention head and time embedding for accuracy. During fine-tuning, we optimize the fMRI projector and elements within the UNet architecture, helping the model learn correlation between fMRI data and image features. Stage B here generates high-quality images consistent with the input fMRI while allowing for individual variability, achieving our goal of accurate and flexible fMRI-based image reconstruction. For image reconstruction, we need paired fMRI-Image dataset. We use two such datasets having 1,000 plots and 5,000 pairs respectively. During data collection, participants in the scanner view images for 9 seconds with 9 seconds intervals. Here, we compare with the previous methods. We found Mind-Vis decoded the most accurate and plausible images with semantically similar details. As the diffusion model is a probabilistic model, we wonder is the diffusion model stable and consistent enough? We see the images generated by our methods were consistent across different variations. We also replicate the result on a replication dataset. We also found that our model decodes extra feature from presenting imaginary thoughts, revealing detailed elements in natural and indoor scenes. Although beneficial, this makes quantitative evaluation challenging, as decoded features might not be corresponding directly to the target images, despite indicating our model's ability to capture high-level semantics. In our study, we found some failure cases where our model were unable to accurately decode certain features from the presented stimuli. We identified two possible reasons for these failure cases. Firstly, it could be due to the subject having thoughts that are not relevant to the presented stimuli, resulting in the corresponding brain activity not being related to the images. Secondly, it could be due to certain features being uncommon in the training set, making it harder for the model to decode them accurately. For example, in one cases where a sock was presented, the model decoded as a sheep. This could be because the model animals are more common than clothing in the training set, and a semantic feature like furry is more likely to be decoded as an animal rather than a piece of clothing. Mind-Vis has certain limitations that needs to be acknowledged. First, the model lacks of strong pixel-level guidance. Secondly, there is no clear interpretation of the feature it learns. Additionally, in the field of general decoding, most efforts focus on individual level decoding and task-specific regions, such as visual cortex. Despite these limitations, Mind-Vis still offers a promising approach to fMRI to image reconstruction with its use of a self-supervised learning framework and biological-inspired design. Thank you for your interest in our work. Please let us know if you have any questions.